All right. You guys at home, if you have any questions, then please put something in the chat. I'll try and check out that chat every so often to make sure that we're all on the same page. All right. So we're going to start off by talking about how to put these square roots, right, into simplest radical form. It's kind of like simplifying a fraction. We're putting something in its lowest terms, and the reason why we're doing it is so it's easier to read. Okay. Now, do you guys remember doing this at all? Okay. So we need our perfect squares, because the perfect squares is what we're really looking for, because we're looking for the biggest perfect square that goes evenly, divides evenly into the number that's underneath the radical. Now, if you remember, a list of perfect squares are numbers like 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. I'm going to stop there, but they do go on even further. If you guys need to have a list of perfect squares handy, feel free, okay? Feel free. I'll probably end up putting a list up on the board. I usually keep that up there through this unit. The nice thing is with the list of perfect squares, if you don't know what it is, you're always going to have a calculator. It's easy to figure out what perfect square is. Just one squared, 2 squared, 3 squared, just keep squaring the next numeral up. So we want to find the biggest number in this list of perfect squares that goes evenly into 48. And when I look at that, the way I figure that out is I figure out what half of 48 is, and that's 24. And then I work my way backwards from there. So 24 would be just in front of 25. So I know it can't be any of these numbers to the right, unless the number is a perfect square. But in this case, it's not. So then I go to 16, and I look and see, does 16 go into 48 evenly? And for us, it does. So I'm going to split this up into 2 radicals. One that's the perfect square, and one that we'd have to multiply that perfect square by to get that number. So 48, I can get that by multiplying 16 times 3. And because 16 is a perfect square, when I take the square root of 16, I get 4 radical 3. That is my simplified radical form. Okay, 4 radical 3. Now, the reason why we do simplified radical form is because it's easier to read. It's a number that's probably more recognizable to us at first glance. But also, when we get further along in math, by simplifying radicals, we're able to combine terms like we would if they were variables. Okay, so at some point in time, we're going to be adding and subtracting radical numbers. And if they have the same radical base, then we're able to add and subtract them like we would if they were variables. All right, let's move to radical 132. So looking for the biggest perfect square that goes into 132. Now I'm going to take 132 and divide that by 2. And that gives me 66. So I'm going to start here and work my way back. Well, I know 64 does not go into 132. 49 does not. So you can see, even on top of my head, I need a calculator just to double check these. Let's see, so 49 does not. Let's do 132 divided by 36. Nope. 25 won't. 132 divided by 16. Nope. 132 divided by 9. 132 divided by 4. There it is. I gotta go all the way to 4. So I'm gonna split this up into radical 4 and radical 33. So this is actually 4 times 33 equals 132. The square root of 4 is 2. The radical 33 stays the same. Okay. So that is our simplified radical form for the middle one. Now when we have a term like we have on the right here, 3 times radical 50, I'm gonna leave this 3 part alone, and I'm just gonna focus on the radical. Okay, so radical 50 is gonna simplify to radical 25 times radical 2, because the biggest perfect square that goes in 50 is 25. The square root of 25 is 5. Now, what you have to be careful of is we have this number on the outside to start. I need to bring that back into the problem. Because now I can actually, you can always multiply a radical times a radical and a number times a number, but you can't multiply a radical and a number and get another number like that, okay? So I can multiply the 3 times 5 and get 15 radical 2. All right, so wanted to, again, I know this is something you guys have already done and learned, but I feel like it's one of those processes that needs to be reviewed every time we go over it again, because we just don't use them all that often. Again, simplifying radicals is a big part of this unit because we're going to be working with right triangles, and right triangles have a lot of radicals within them, right? Based on specifically Pythagorean theorem and distance formula and things like that. Move on to, now this unit is actually unit 7, and this is 7.1, okay, Pythagorean theorem. So we're going to be focusing on using the Pythagorean theorem throughout this unit. And this whole unit is based on right triangles. So it's not only going to involve Pythagorean theorem, but it's also going to involve trig, right? Because we're going to be working with sine, cosine, and tangent, and using trig functions within our unit. And we'll also be doing some application-based problems that go with them as well. All right, now, you guys, probably one of the first formulas that you guys remember when you're younger, Pythagorean theorem, a squared plus b squared equals c squared. Okay. So we'll probably be able to go through this pretty quick. A squared plus b squared equals c squared. So it's just taking our 3 sides where a and b are represented as the lengths of each leg. Okay, and the legs are the sides that come off of the right angle. C is always the hypotenuse, always the longest side. This is just the written out version of our equation. In a right triangle, the sum of the squares of the legs is equal to the square of the hypotenuse. All right, so here we're given 2 leg lengths, 7 and 24, and we want to find C, our hypotenuse length. So we take 7, 24. So we got 7 squared plus 24 squared equals C squared. Having a calculator handy is helpful. 7 squared plus 24 squared, I get 625. So 625 equals C squared. To get our final answer, I need to take the square root of both sides. And this is where simplifying our radicals is going to come in handy. I know that this cancels out the square part and the square root part, so I'll get C equals. Then I got to simplify radical 625.
Well, that's a perfect square.
625 is?
Yeah, it's 25.
And that would be a good starting point, is see if the answer you get is a perfect square. If it's not a perfect square, then we can kind of divide it in half and we can work our way down the perfect square list. But if it is a perfect square, bonus. Now we don't have to worry about simplifying a radical. All right, just take the square root. Every calculator has a square root symbol on it. All right, so if you're not sure if it's perfect square, just plug it in and take the square root. I know you guys have the emulator for these calculators on your Chromebook, or you have access to them. If you're not sure where that link is, it's in important links that I have in Google Classroom. You guys can put that on your Chromebook. I really like using these calculators because these are calculators you guys are going to have access to for your math classes in high school and in college. Right? They'll let you use these types of calculators. So some of the more advanced calculators in this, they will tell you you're not allowed to use them, okay? Because they do, not that they do the math for you, but they allow you to do more advanced math that they want students to be able to prove they can do on their own. Okay, here's one where we got A equals 9 and C equals 41. Right, so this is one where we're given a leg and the hypotenuse. Right, so we're going to set this up a little different. We got 9 squared plus B squared equals 41 squared. It's 81. 41 squared is a really big number. It's 1681. When I subtract, because I want to get B squared by itself, I can't solve this until I have B squared by itself. When I subtract 81 from both sides, I'll get B squared equals 1600. And this is another perfect square. B equals 40. These are actually what we call the answer, the sets of lengths we've used so far. These are called Pythagorean triplets, okay, because they're whole number side lengths. Okay. There's a lot of these, but there's not a lot of them that have really small numbers or smaller numbers like this. Okay. But these are examples of Pythagorean triplets. All right, here's where we got A equals 5 and B equals 10. You solve for C. We got 5 squared plus 10 squared equals C squared. 25 plus 100. 125 equals C squared. I take the square root of both sides. All right, I'll get C by itself. Let's see, 125 is not a perfect square, but I know 25 goes into 125. And it goes into 125 5 times. And the square root of 25 is 5. So I get 5 radical 5 for my length for C. Okay. Now, there are some times that we'll say, give us the length of the missing side rounded to the nearest 10th. If that were the case, then right here, I could take the square root of 125 and get my decimal answer that I can round. Okay, I wouldn't need to simplify the radical and then find it. Now, a decimal solution is not an exact solution. It's estimated, which is why if we want an exact answer, we have to simplify the radical. Yes, sir.
How do you do the square root on the calculator?
It's probably on that one, you probably hit the second button and then the square button.
What?
where's that's the root. So that'd be more than a square root. There it is, see the square button right there? See the second square.
So,
See the second. Got it? All right. A equals 3 and C equals 7. A equals 3, C equals 7. So we got 3 squared plus B squared equals 7 squared. 3 squared is 9. 7 squared is 49. If I subtract 9 from both sides, I'll get B squared equals 40. All right, radical 40, I'm going to do this up here. The biggest perfect square that goes into 40. I feel like it should be higher than this, but it's 4.
yes.
And 4 times 10 is 40. So B is going to equal 2 radical 10. 2 radical 10. Yes. I think we still do those passes. All right. Now, we've got a few more examples, and these other examples deal primarily with some of these type of problems where you have radical lengths. Okay, so we're going to get a little bit of practice working with squaring things that are already radicals. All right, so A equals radical 6 and B equals radical 3. We're going to do the same process. We got radical 6 squared plus radical 3 squared equals C squared. When you square a radical, you are undoing the radical. Okay, you're undoing it. So radical 6 squared equals 6. Radical 3 squared is 3. And 6 plus 3 is 9. When you take the square root of both sides, 9 is a perfect square. So C is going to equal 3. Okay. I like when you square radicals because it undoes that radical. It makes the problem a little bit easier to work with. Okay, so there's an example where by squaring these, we got 6 plus 3, which equals 9. And when we take the square root of 9, we get 3. If you've got a number times the radical, when you square it, this you need to be careful of. So A equals 3 radical 3. B equals 2 radical 5. So I'll get 3 radical 3 squared. 2 radical 5 squared equals C squared. Now, you'll notice how I put those in parentheses. Okay? And that's because if you, in your calculator, if you were to multiply 3 radical 3 squared and you don't put a parenthesis, it'll do the radical 3 squared first and give you 3. And then it'll multiply it times the 3 that's outside the radical. So you get 9. But if you were to put it in parentheses, because we should be squaring the entire length. When you square this, you actually do the 3 squared, which is 9, times radical 3 squared, which is 3, and you get 27. 27 is correct here. Okay? So when we're squaring this, you're actually squaring both parts inside the radical. Which is why when you use a calculator, put that length in parentheses. So we get 27 there. 4 times 5, we get 20 here. 27 plus 20 is 47. All right, now here is an example. When I take the square root of both sides, I get a radical 47. You can't simplify that. Okay? In fact, I think 47 is a prime number. You cannot simplify the square root of 47. There's no perfect square that goes into it. If that's the case, it's already simplified. Okay? And you can verify that by, again, if 47 is not a perfect square, when I divide 47 in half, I get 23.5. If I look at all the perfect squares less than that, 16, 9, and 4, none of them go into 47, then you're there. You're already at your simplified answer. Right, last one. And here's an example where we can find our value to the nearest tenth. But in order to find our length here, we've actually got to use the Pythagorean theorem twice. Okay? And that's because if we want to solve for x, we would need to focus on this red triangle on the right, which is a right triangle, but we only know one length right now. Okay? So we need to find this other leg's length in order to then focus on the red triangle. So to start, we're going to go ahead and focus on this green triangle. And I'm given a leg and the hypotenuse. So we'll call that A, and this B, and this C. So I get 6 squared plus B squared equals 7 squared. 36 plus B squared equals 49. When I subtract 36 from both sides, I get B squared equals 13. I took the square root, I don't need the square anymore. I'll get B equals radical 13. All right, that can't simplify. So I'm going to leave it like that for right now. So this length right here is radical 13. Now I'm going to focus on the red triangle. I'm given the 2 legs. We'll name this, we'll say A equals 4 and B equals radical 13. X is going to represent our C, our hypotenuse. So we're going to get 4 squared plus radical 13 squared equals x squared. 4 squared is 16 plus 13 equals x squared. So 29 equals x squared. To get my final answer, I'm going to take the square root of 29. And I get 5.385. Now we want it to the nearest 10. Taking the square root of both sides, we get x equals 5.4. Okay. Now, I give you guys a little bit of leeway on this one because if we were to have done radical 13 and gotten like this length to the nearest 10th, and then use that to square things and get our final answer, our answer might be off by a 10th or 2 because of where we're rounding and when we're rounding. Okay, but I give you guys a little leeway on that. Like I'd probably let you guys give an answer anywhere between 5.3 and 5.5. All right.